Hello friends, welcome again to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss a problem which has been a mass spectrometry problem which has been asked in the CSIR NET December 2019 examination. And along with this problem I will also cover the mass fragmentation pattern of the aromatic compounds, right? Like your aromatic amides. Okay, so right now on your screen you can see here the problem is given in that manner. The compound that shows the peaks in the EIMS at m by z value of 121, 105, 77 and 44, and you have been given the four compounds and you have to select the compound which is actually consistent with this given mass fragmentation pattern. Okay, so for this first of all you have to understand the thing, which peaks which compounds out of these four, which compounds will give actually the peak at 121, that is m by z. So if you carefully look the examples, so the molecular formula for this first one is C7H7NO. Okay, and the same molecular formula is for the second compound also. Okay, and for third compound you are having say C8H11N, and for your fourth compound is C7H7N and O. So these formulas are given. So if you actually calculate the total weight of all these ions, so molecular weight of this ion, say I am writing MW, molecular weight for this, it is 121. Okay, and for the second compound also the molecular weight is 121, and this 121 is true for all the given compounds. Okay, so that means all can give the peak at 121, so it is not very helpful for us. Okay, now we will look at the second peak, which is actually this particular one. If you see here, right, this 105 peak. Okay, this one. Okay, so we will focus on this particular one, 105. How we can get this 105 peak? So for this what we will do, we will take 121 from here and will subtract from this 105. So if you subtract 105 from this, then you will get the 16. That means removal of 16 mass unit is important. Removal of 16 AMU I can write. So you have to remove 16, and you know the 16 correspond to the removal of the NH2 group. You know nitrogen is 14, one hydrogen is 1 times 2, right? And if you solve this, that will give you the 16. So from these compounds you have to remove your NH2. So which options would be the correct one? So you can focus on this option C here. You can focus on this particular compound, right? This option C. So there is no way in this particular option C by which you can remove the NH2 from here, because you can see here this is CH3 and this is also CH3. So you cannot remove CH3 NH2 from here. So this C cannot be your answer. Okay. Now if you focus on your another example, say another structure, which is this one, the option D, you can actually follow my cursor. Okay. So in this option D again you can see there is no way by which you can remove the 16 mass unit, that is NH2 cannot be removed from here, because the structure will not permit actually to remove will not allow to remove the NH2 from here. So this D cannot be your answer, so you can strike out your D also. Now you left with the A and B. So out of A and B you have to select the correct answer. Now what you can do here, say for example I am fragmenting this particular one, option A. If you fragment, if you take the fragmentation of this particular part, so what it will give you, it will simply give you, say if you remove NH2 radical from here, so it will give you what, phenyl, this particular one, and this attached CHO. And if you calculate the total weight of this particular fragment, so this would be your C7, okay, H6 and O. So 12 sevens are 84, 84 plus 6, 90, 90 plus 16, that will give you 106. So you will get the peak at m by z 106, but you are having the peak. You can see here in the question itself it is given that you have to find the peak at 105. So from the first compound you are not getting the peak at your 105, rather you are getting at 106. So you can strike out the option A also. So automatically your correct answer is option B. Okay, so how we can go for this option B, and how we can take the different kinds of the how we can actually make the different fragments from this. So I am telling you how you can do that. See the fragmentation pattern here. So for this I am changing the color. Say this is your compound, okay, this is C double bond O in H2. So first of all it will form a molecular ion, and you know the molecular ion, two lone pairs were already there on it, and one will be ejected out by the electron impact. So this fragment is basically your molecular ion, and this correspond to the 121. Now you can do the fragmentation pattern of this one. Alpha cleavage would be the preferred one, okay, and when alpha cleavage is the preferred one, so simply what you can do, you can break this particular bond from here. So one electron will come out just like that, okay, and one electron will go over there, clear. And from here you can remove your NH2 as radical. Now what you left with is, this is your phenyl, okay, and this is carbon. Double bond was already there, and one electron, odd electron is already here, and one electron is coming from and another electron is coming from basically this fragmentation pattern, okay, from this fragmentation it is coming. So this is actually your carbon triple bond oxygen, okay, and over there a positive charge. So if you count the total weight of this particular fragment, it is up to you, right? I am not counting it, but I know it is having the m by z value of 105. So it is giving the m by z value of 105. So you have to actually identify, you have identified your 121 and 105. So this is the consistent one. Now whenever you are having the phenyl compounds having this carbon triple bond oxygen, a very famous fragmentation pattern in these cases would be just like that. You have to remove actually the carbonyl from here. So what you will do, you will remove the carbonyl from here, okay. So how this will go there, and the lone pair will go there, and you will have CO negative, and then you are having this phenyl cation. Phenyl cation is simply what? It is your C6H5, okay. That means 12 into 6 is 72, 72 plus 5, that is 77. So this phenyl cation is basically is the m by z 57. This is how you can actually write, okay. And after that, see, you now you have explained this one also, and now the fragmentation pattern, you see the fragmentation is very easy when actually you want to show the another 44 peak. So how you can show the another 44 peak from this phenyl cation? So you can check in that manner. Say you were having this structure, this was your phenyl cation, okay. Say I am putting positive here, see, you can put positive anywhere, okay, there is no problem in that. So what I will do here, I will break this particular bond, I will break this particular bond. So one electron would come here and another electron would go there. From here one electron would come here and another electron would go there, and then you are having your species, the fragment, right, that fragment. See, this double bond was already there. So let me change the color. This double bond was already there, and see, you can focus here. One electron is coming through with this fragmentation, another electron is coming through this fragmentation pattern, and you know the pair of electron is what? It is simply a covalent bond. So this is a fragment actually, right, which is what? Carbon along with the two hydrogens. So what you left with in that case, left with this double bond was already there, 2 double bonds, and if you check again, one electron has shifted through this fragmentation and another electron has shifted through this fragmentation pattern. So what you will do, you will put odd electron here, odd electron here, and these two odd electrons actually will combine in that manner, and this is actually identical to this particular cation, okay, and this is having what, m by z value of 51. It is a very special feature, m by z, at m by z 51 you are getting this particular peak, okay. Now if you go back, you see here, see 44 is given, but these three are sufficient, but this fragmentation is incomplete actually without the formation of the that 58, okay. So this is something very, very important. Now if you closely look the mass spectrum of this particular compound, it is looks like this one. So in this this problem of your CSI, this 2019 December CSI and NET examination is taken straightforward from here. So you can focus your on your peaks actually, right? How you can focus on your peaks? First of all, you were getting at 121, second was 105, second one, third one is 77, and another one is 51, which I have explained to you, okay. And this problem actually straightforward taken from the spectroscopy, organic spectroscopy by Jagmohan, organic spectroscopy by Professor Jagmohan, okay. Narosa publication. So they have lifted this problem straightforward from this particular compound, okay. Now if you go back little bit, okay, say, right, so you have struck out all the options here, so there is no need to go back actually. This is how you can explain this. So this is the mass fragmentation pattern of your aromatic aldehydes, but with this problem actually I want to solve one more problem. You can see this problem here, which is again, see the compound is basically, it's the same type of the compound, okay. The only difference is that, see, in the earlier case you were see, if you check, in the earlier case you were having hydrogen here, in the earlier problem you are having this structure, NH C double bond O H, okay. No, this was not the problem actually, this was actually, no, this was just like that, C double bond O and then NH2, this was the problem. But now you are having what, you are having this hydrogen substituted with this one. So this compound is basically your acetanilide. So you have to see, you can also explain this acetanilide, the formation of these peaks, how actually these peaks are forming in that case, again you can very easily show. So but in that case, see, it is sufficient if you explain some of the peak, right, like 66 you can explain very easily, you can 93 you can explain, and you can also explain this 135, okay. So how we can explain these peaks, you can see here. So first of all I have to clear something from here, how actually the fragmentation pattern is going on in that case. So I am writing it, writing this here actually. So you are having this structure, the benzene ring, just like that, and say I am writing this, see I need some space, so I am writing in that manner. This is C double bond O and this is CH3. So I am putting all the hydrogens over there. So if you want the fragment, if you want the ion from here, so what you can do, you can knock out one electron from here, you can put positive over there, okay, and in that manner you are having this peak at m by z 135, because the molecular weight is 135. So next peak you are getting at the 93. So what you will do, you will take this 135 and you will subtract 93 from here. So when you subtract 93 from here, then you will have 2 and 42. That means you have to remove the 42 mass unit from here. So what this 42 mass unit is, you have to understand this thing, and this is quite complicated and very interesting one also. So in that case, you can see here, if you consider this nitrogen is alpha part, and this part is the beta part, and this part is the gamma part. However, this is not a good way of writing alpha, beta and gamma, but you can write in that manner. So how actually the fragmentation would occur in that case, you can see one of the electron, this double bond actually will break, one electron will shift here, and this hydrogen along with the one electron will come here, okay, and another electron will go to this particular position, okay. Now what you will do, now check this one, this fragmentation would occur. Now this bond will break and one electron will shift on this nitrogen, okay, and one electron will shift on this particular nitrogen. So what basically is happening here, this hydrogen is shifting at this particular position. So what fragment you can have here? You can have this fragment. This and one hydrogen actually came from this methyl and one was the hidden hydrogen on this phenyl part. So what you can do, you can write another hydrogen here. So two hydrogens are there, and now you can see here this bond has broken. So one electron actually is coming from here, okay, and another is coming from here, this one. So this just like that. So you can put a double bond here, okay, and then nitrogen and the hydrogen dot and positive, okay. So this ion is basically what? This is see, this is what? This is actually non-aromatic compound. This is non-aromatic, but the earlier one is aromatic. So this compound will regain its aromaticity. So how it can regain its aromaticity? It's quite easy. Out of these two bonds, one electron will come here and one electron will go there, and this hydrogen will push one electron here, and this hydrogen along with the one electron will move to this nitrogen. So what you will have? Regain of the aromaticity, just like that, okay, and then you are having the NH2, and a positive is already there. So this cation is basically what? M by Z equals to 93, and it is what? Resonance stabilized. Resonance stabilized. So that's why it is the base peak, okay. So this phenyl, this peak you can explain in that manner. Now it's very easy. From here what you can do, you can remove one of the NH2 due to the alpha cleavage. So you will have your phenyl cation. Earlier, in the earlier case, I have also drawn this phenyl cation, okay. You can put positive here. This is what? M by Z 77. However, the 77 is not, see, this is here actually. This 77 is here actually, okay. And then you are observing the see peak at 66. Now you can go for the peak at 66. So how you can go for the peak at 66? I am writing it again here. You can see I am drawing the structure again here. Okay, this was the structure, two of the hydrogens, okay, and double bond NH dot positive. Actually this structure is this particular one, right? This structure I have written again here, okay. Now in that case what you can do, you can very simply remove the HCN molecule, hydrogen cyanide, okay. And when you are removing the hydrogen cyanide from here, it simply means what? Say this, actually this particular bond, this one, this will break and this will join this carbon. So this is 1, this is 2, this is 3, this is 4, this is 5. So you are having only 5 membered ring, just like that. And 2 hydrogens were already there at position 1. So you can write 2 hydrogens here, of course, and somehow you can put the positive and dot over there, and your SCN will be removed from here. See, N is here, H is here, carbon is this particular one which will remove from here. Okay. So if you remove, then if you can count then you can count the M by Z value of this one. This is actually your 66. So this 66 peak is there actually. Okay. So this is how. See, you can also explain this CH3CO, the formation of CH3CO, but this peak is not very significant one. It is not a diagnostic peak. So this is how you can explain the splitting pattern of your aromatic amides actually, right? So that's it for today, guys. Say if you understood the problem well and the explanation. Then if you like the explanation, please subscribe the tetrahedron chemistry classes. Okay, and don't forget to like the video and share your friends also. Okay, share with your friends also. Thank you very much.